Welcome to APC Kinematics Episode 1.0. The C is for Calculus. This episode is going to involve derivatives and integrals, so you need to know the basics of those. And also, I highly recommend, if you haven't taken any physics before, or it's been a little while, to head over to my other channel, Learn Physics at Home High School, and look at episode 1.3, One-Dimensional Kinematics. I will put a link in the description. And if you enjoy this content, be sure to like and subscribe. So we need to define a few things before we can start to solve kinematics problems. Kinematics just deals with motion, and this first episode deals with one-dimensional motion, or motion in a line. We're going to start by horizontal motion, and then we're going to deal with dropping objects and throwing objects up in the air, and that's going to be also one-dimensional motion. So the first letter that we need to know is x. And x is either distance or displacement. So distance is defined as the total path traveled. So if you go for a walk and you walk a distance of 20 meters to the right and turn around and come back 10 meters to the left, your total path travel would be 20 plus 10, or 30 meters. Displacement, however, is the straight line distance from start to finish. But it's a vector quantity, which just means it has to include direction. So, if we define here to the right as positive and to the left as negative, our displacement is the straight line distance from start to finish. So that would be 10 meters to the right, or positive 10 meters. In calculus, the change in x, which we can call the displacement, and sometimes we just leave that as x, defining x as displacement, but the change in displacement is the integral of velocity with respect to time, and we'll do that coming up soon. V is either speed or velocity. Now, speed is defined as distance over time, and that just tells us how fast something is moving. Whereas velocity is defined as displacement over time, and that tells us how fast, but it also tells us direction. So speed is a scalar quantity, whereas velocity is a vector quantity. If we want to find the change in velocity, we take the integral of acceleration with respect to time. Now, there's different velocities we have to pay attention to. V inst is the instantaneous velocity. In other words, the velocity at an instant in time. V naught is the initial velocity. Vf, that's the final velocity, and delta, the Greek letter for change, is the change in velocity. Now, acceleration, measured in meters per second squared, is how velocity changes. So it's the rate of change in velocity. Now, because velocity is a vector, we normally think of acceleration as speeding up, but a change could also be slowing down. So in physics, it's important that we understand that acceleration is a change in velocity, this vector quantity, and velocity includes direction, so this could also include a change in direction. For example, going around a corner or traveling in a circle. So A inst is the acceleration at an instant. So that's how fast it's changing its velocity in time. And that is defined as the second derivative of position, or we could say the first derivative of velocity with respect to time. Going back to this v instantaneous, I forgot to mention, this is the first derivative of displacement, or dx over dt. So the first derivative of displacement is velocity, and the second derivative of position, or the first derivative of velocity, is acceleration. Now we have a whole bunch of equations that we deal with in kinematics, one-dimensional kinematics, and the first is the average velocity. The average velocity is displacement over time. Or we could also define average velocity as the final plus the initial divided by 2. When the acceleration is constant, we can use any of these three formulas. Acceleration is defined as the change in velocity over time. But if we rearrange this formula and say that the change of anything is the final minus initial, we can put that in for change in velocity, rearrange the formula, and get Vf equals V naught plus At. Another very useful formula is to find the position based on the initial velocity and the acceleration. Now, in this formula, it's written on the AP reference table as x, without the final, equals x naught plus v naught t plus 1/2 at squared. But if we subtract this over to the other side, that gives us delta x. Now, on the reference table, if it's written just as x, and you understand that to be delta x, then x is defined as the displacement. And finally, we have Vf squared equals V naught squared plus 2a delta x. This is the displacement. And what's nice about this formula that is not in any of these other formulas is that there is no time. So this formula is quite useful when we end up with a problem where time is not given. Let's go ahead and put some numbers in and solve a couple of problems. So let's say we have a little cart, and this cart drives to the right 10 meters and turns around and comes back 2 meters. The first thing we need to do is define our directions. So let's call to the right positive and to the left negative. The total time for this event is 2 seconds. So to solve for the average speed, we are going to do V average, that's what the little line is for, equals x over t. But remember that when we're dealing with speed, x is distance, and distance is the total path traveled. So 10 plus 2, that gives us 12, and the time is 2 seconds, so that gives us an average speed of 6 meters per second. For the velocity, velocity is displacement over time. So where is the car after 2 seconds? It is 8 meters to the right from the origin, which is where we started. So when we do displacement, we're going to say 8 meters, notice that's plus to the right, over 2 seconds. So our average speed is going to be velocity is going to be 4 meters per second. And we don't have to write this plus, but I'm going to put it in there because it came out positive, telling us that our average velocity is to the right. So let's go ahead and do this comparing two different cars. One car that's traveling at a constant velocity, and a second car that starts at rest and speeds up. So in the first case, the car is traveling 10 meters per second the whole time. So we can use this velocity formula as a constant velocity formula. So we can say at 10 meters per second, that's equal to x. X is what we're going to be solving for, and for 10 seconds. So we can see that when we multiply through, x comes out to 100 meters. So that distance has been determined by the average velocity in the time of 10 seconds. So what's it going to be for the cart? Well, the cart's accelerating. So it starts from rest, so V naught is 0. 0 times 10 is 0. So now we can say x is equal to 1/2 a, which is going to be our 2 meters per second squared, times t, which is going to be 10 seconds squared. 1/2 times 2 is 1, 10 squared is 100. So in both cases, the cars end up traveling 100 meters. What's that going to look like on a graph? Well, let's take the car at a constant velocity first. The car at a constant velocity is traveling along at 10 meters per second. They're traveling 10 meters per second for the entire time t of 10 seconds. So the second car is traveling from an initial velocity of 0 and speeds up until they're going 20 meters per second at the end of this time. How do we get that 20 meters per second? Where did that number come from? Well, we can use our other formula, Vf equals V naught plus At, and we could say that the initial velocity is 0, so that's going to be A, 2 meters per second squared times 10 seconds, so that's where that 20 meters per second comes from. Okay, so let's first look at a couple of things about slope and also the area. Now, we know that slope is equal to change in y over change in x. So if we do change in y over change in x, we can actually say that delta v over delta t is going to be equal to a. So the slope of a velocity time graph is the acceleration. Well, let's put some numbers in there. Our numbers would be 20 divided by 10. So what's 20 divided by 10? That would be 2, and the slope is the acceleration. So the acceleration is the slope of the line. The slope of the other line is 0. Now, if the acceleration is 0, it means its velocity is not changing, therefore its velocity is constant. An acceleration of 0 can also mean that the object's not moving at all, but in this case, it's moving at a constant velocity. And finally, we can also say that v is equal to x over t. So therefore, x is going to be v times t. Well, let's take an example of this constant velocity situation right here. So the velocity change is 10, and the time is 10. So the velocity times the time is the area underneath the graph here. Well, what does the area equal? The area is equal to the displacement, v times t. So let's see if that makes sense. We have 10 times 10, that would be 100 meters, and that's the distance that it traveled. Forces are another unit that we're going to be covering in a later episode. But we need to understand forces, specifically net forces, so that we can understand acceleration. So the definition of a net force is mass times dv over dt, the derivative of velocity with respect to time. But we know that that is the acceleration. Net just means the vector sum, or we could say the total. So let's look at a couple of examples. The first one, we have no forces at all. So what's the total vector sum? What's the vector total sum of those forces? There are no forces, so it's 0. That means that the acceleration must be 0. There's no net force, so there's no acceleration. If there's no acceleration, the object could be doing two things. It could either be at rest, not moving, or its velocity could be constant. This is also called equilibrium, a state in which the total forces equal 0. We could also have equilibrium with forces if the forces cancel each other out. So let's say we have a force to the right and a force to the left that are in equal magnitude but opposite directions. When we subtract them, the vector sum is 0. So in this case, the object could be stopped or its velocity could be constant. But what happens when the forces are unbalanced, where we have a vector sum equal to something other than 0? Well, we subtract those forces. And whatever the leftover force is, that's the net force. In that case, the acceleration is not 0. It's something. And I'm just writing something. It could be 2 or 8 or -5. It could be any value other than 0. In that case, the velocity is changing. That's what acceleration means, velocity changing. And finally, if we have only one force, the net force is that individual force. So we have a net force, so acceleration is something, so therefore v is changing. We have to pay close attention to the direction. So if the net force is to the right, then the acceleration is to the right. The acceleration is always in the direction of the net force. A is always in the direction of the net force that causes the acceleration. Why is this important in kinematics? Well, let's say we define to the right as positive and to the left as negative. And let's say we have a block that's moving to the right. If we apply a net force to the right, we know that the acceleration also has to be to the right. So what's this object going to do? If we have a net force pushing it this way and it's moving this way, it's going to speed up. So we say when A and V are in the same direction, the object is going to speed up. But what happens if the object was moving to the left while we were pushing it to the right? In this case, the net force is to the right, so the acceleration is to the right, but the object's moving to the left. When A and V are in opposite directions, it will slow down. So here's a tricky concept. Can you have a negative acceleration while it's speeding up? Sure. What if we are pushing it to the left and it's moving to the left? The net force is negative, so the acceleration is negative, and if it's moving to the left, its velocity is negative. These are both negative, the acceleration and velocity are in the same direction, so the object will speed up. Let's put some numbers in so we can see more closely what's happening. Let's say we have a car that starts at rest, and it accelerates at 2 meters per second squared. What that means is every second it will go 2 meters per second faster. And it does this for 10 seconds. How far does it go? Well, we could write our formula delta x equals v naught t plus 1/2 at squared. We know that the initial velocity is 0, so delta x is going to be equal to 1/2 2 times 10 squared, or a displacement of 100 meters. How fast is it going? We're solving for Vf. Well, we can do that with Vf equals v naught plus at. And we know that the initial velocity is 0, so our acceleration is 2 times 10 seconds, and that's going to give us a final velocity of 20 meters per second. We could also have used this formula, and I'm only showing this to you so that we can get a little bit of practice doing all three of the main formulas. This one doesn't depend on time, which is nice. The initial velocity is 0. We have 2 times 2, and delta x. And that delta x we know from the first problem was 100 meters. And so our final velocity comes out to 20 meters per second. Either way, you'd get the same result. Okay, what is that going to look like on a graph? Well, in terms of the displacement, let's look at what's happening. Now, I picked the number 2 because it's nice, because we're multiplying it by 1/2. So the initial velocity is 0, so this drops out to 0. So our formula for how far it's gone, or its displacement, is just 1/2 at squared. And 2 times 1/2 is 1. So the displacement is not just directly proportional to t squared, it's equal to t squared. So how far does it go in the first second? 1 squared, a meter. 2 squared, 4. 3 squared, 9. 4 squared, 16, and so on, all the way up to 10 squared equals 100. So what's happening here in our graph? Well, up to 10 seconds, and our displacement of 100 meters, it's growing exponentially. So it's curving up like this, reaching 100 meters at that point. And what's the velocity doing? Well, the velocity is increasing by how much? 2 meters per second squared. It's increasing by 2 meters per second every second. So eventually, by the end of 10 seconds, we know it will be going 20 meters per second. This increase of 2 meters per second every second that goes up is a constant value. It's constantly going faster. How much is it constantly going faster by? It's constantly going 2 meters per second squared faster every second. So here's a question. At 5 seconds, what is the velocity? What's the acceleration? What's the change in velocity? And what's the change in position, or the displacement? So to figure out how fast it's going at 5 seconds, we can do the slope of the line. The slope of the line right there is the derivative of that point. That would be our dx and our dt. So slope is x over t. Instantaneously, it is dx over dt. So we have to take the first derivative of x. Well, what's x? The initial velocity is 0, so we can shortcut this into 1/2 at squared. And we know that this is 1/2 times a, which is 2t squared. That becomes 1. So we're taking the first derivative of t squared. What's the power rule for t squared? It's 2t. So the velocity is the first derivative of this, which is 2t. So how fast is it going at 5 seconds? At 5 seconds, it's going 10 meters per second. That is the slope of the line right there. The slope of that line is 5 meters per second. The next question was, what's its acceleration at 5 seconds? Well, its acceleration is actually constant, so all we have to do is at 5 seconds find the slope of the line. Well, that also happens to be the slope at any moment in time, so we sort of could do this anywhere. We don't have to do it at 5 seconds. So if we look at our formula, we have the slope of velocity with respect to time. That's dv over dt, or the instantaneous acceleration. And we know from before that velocity is equal to 2t. So all we have to do is take the first derivative of v. What's the first derivative of 2t? Well, that's just 2. So the acceleration is 2. There's no time involved, so the acceleration is 2 meters per second squared the entire time. Now, we know that the area is equal to the integral of a with respect to time. So the change in velocity is going to be integrating on a. Well, what's a? A is 2. So we're going to integrate, but we need to do this with the bounds of 0 to 5. We're starting at 0 seconds, we're ending at 5 seconds. So that's going to be the integral of 2 dt. Now, you might not know this if you haven't gotten this far in calculus, but that's essentially going to be 2t to the 0, because we have a t there, we're integrating on t, but it would just be the number 1. So we add 1 and divide by the new exponent. So what's that going to give us? What's the area of A? That's going to be a change in velocity of 2t. But we need to apply our bounds, our final and initial values. So From 0 to 5, that's going to be 2 times 5 minus 2 times 0, or a change in velocity of 10 meters per second. What have we just found? Well, the first derivative of position and time was our velocity. The slope of velocity versus time was our acceleration. But now we're doing the area. The area is the integral of acceleration with respect to time. So that's going to be the change in velocity. How much did it change its velocity from 0 to 5 seconds? Let's look at the graph. 0 to 5 would be 10 meters per second. And finally, if we want to find the displacement, we know that displacement is the integral of velocity with respect to time. So we integrate the velocity formula, which we know from before was 2t. And what's the integral of 2t? Well, we're going to add 1 to the new exponent, which is going to be 2, divide by the new exponent. 2 over 2 is 1. So our change in displacement is going to be equal to t squared. So how far did it go in that much time? From 0 to 5, that's going to be 25. And where is that on the graph? That's going to be this triangle right here. The area of this is our integral that lets us know how far it went. We can check this by looking at the formula delta x equals v naught t plus 1/2 at squared. The initial velocity was 0 times a time of t, which doesn't matter because that's 0, plus 1/2 times 2 times 5 seconds squared. So 2.5 cancel, and we're left with the same answer, 25 meters. Let's look at one final example, but this time it's going to be a car that was already moving and slowing down. So we have this car that's moving at 20 meters per second, and it's slowing down. Now, if it's slowing down, something must be pushing on it this way. Specifically, this is the brakes pushing on the tires, and the tires pushing on the road, and the equal and opposite force of that is friction pushing on the car this way. We'll deal with the specifics of that net force later, but all you need to know for now is that the car is moving this way and being pushed this way. If we call to the right positive and to the left negative, then our net force produces an acceleration in the direction of that net force. So we have a negative net force producing a negative acceleration. So it travels some distance x, and we're going to look for that x, find x, and then also how fast is it going at the end of this time. So it starts at 20, we don't know how fast it's going, it's accelerating at -2 meters per second squared, and it's going to take 10 seconds for this to occur. So we can start out with our kinematics equation, x equals v naught t plus 1/2 at squared. And this time it does have an initial velocity. So we say 20 times 10 plus 1/2 times -2 times 10 squared. And that's going to give us 200 minus 100. So x is going to be positive 100 meters. In other words, it's traveling to the right 100 meters. Well, how fast is it going at the end of this time? Vf equals v naught plus at, and the final velocity is going to be equal to 20 plus a -2 times 10 seconds. Well, that's going to give us -20, so it stops. Lastly, although we figured out that the horizontal position was 100 meters, I want to show you that we could have also done it this way. The average velocity is equal to Vf plus V naught over 2. And since it started at rest and uniformly accelerated, then we can say that the average velocity, was 10 meters per second. It was averaging 10 the whole time. Well, if that's true, then we can do v average equals x over t, and we can say that 10 meters per second is equal to x over 10 seconds, and we get the same answer of 100 meters. So let's look at what's happening in terms of the displacement, the distance from the start position. So if we use this formula, we can say at 0 seconds, initial velocity, 1/2 -2 times 0, is just going to be 0. In other words, when the problem starts, it starts at 0 meters. That's our origin. After 1 second, if we plug the numbers in, after the first second, it's gone 19 meters. After the second second, it's gone 36 meters, and the third second, 51 meters. But what's important to notice here is the change. It went a change of 19 in the first second, a change of 17 meters in the next second, and 15 meters in the next second. So what's happening? The distance that it's traveling is decreasing each second. So what would that look like on a graph? It's covering less and less distance in time. Now, similarly, we can look at the final velocity. So we can say that Vf equals V naught plus AT, and I'm just going to rearrange this to put Vf on the other side. So we can say V naught plus AT is equal to Vf. So if we start, we say it starts with 20 plus -2 times 0. How fast is it going at the end of 0 seconds? 20 meters per second. How fast is it going at the end of the first second? Well, that's going to be -2 from 20. That's going to be 18 meters per second. And 20 plus -2 times 3, that's going to be, sorry, not 3 seconds, 2 seconds. Going up 1 second at a time. That's going to be 16 meters per second. And we'll just do it one more, -2 times 3, and that's going to give us 14 meters per second. So the velocity is decreasing. What's the velocity decreasing by? It's decreasing by 2 meters per second every second until it stops. But I want you to notice something else. The change is 2 in each case. And it's negative because it's decreasing. So what's constant? A constant negative acceleration. It's constantly losing 2 meters per second every second. So let's go back to this idea of derivatives and integrals. The first derivative of x and t is going to be the instantaneous velocity. So if we look at the velocity right here, the slope of that line would be equal to the velocity at whatever time we pick that to be. When we get to the top, the object has stopped, so the instantaneous velocity would be equal to the slope here, which would be 0. When we started, the instantaneous velocity would be equal to the slope here, which would be 20 meters per second. Now we know that the slope of a velocity time graph is equal to the acceleration. So what's the slope of this line going to be equal to? It's going to be equal to the acceleration. The slope is going to be equal to -2 meters per second squared. Finally, we can work backwards. We know that the integral of area is the change in velocity. So that area down here is going to be equal to this. And that area is going to be equal to the change in velocity. And the integral of velocity is going to be equal to our change in displacement. So if we take the integral of that, that would be this area. That area would be equal to the displacement on this graph. Specifically, it would be 75 meters.